Okay, so the main objective of this lab report was to model the system of a ball falling just from a height, and the idea was to try and model it using the forces of gravity and the forces of drag. The results from the experiment found that the system cannot be properly modeled without the forces of drag because the ball just keeps going too fast for too long and never reaches a terminal velocity. So this video I have right here is me in a window, and I've got an orange in my hand. Now, the video is sideways because of how it was recorded, so I've flipped the axes around so that, one, the orange will start at the origin, and this axis right here is actually in the negative y direction. So this way it would be falling in the negative y direction. The beginning is right here, right before I let go, and the end is right before it hits the ground. The time is 1.2 seconds. And here is the video. You can see the red circles are where I'm tracking the orange falling, and here it stopped right before it's going to hit the ground. Now, the same thing was done for another video, except this time instead of an orange, I used a balled up sock. This way when it falls slightly slower and even got blown a little to the side by the wind. But you can see the same thing here. I've set up my scale right here based on the size of the sock, as I did in the other video with the size of the orange, to get the proper scale so that Tracker can collect all this data for me. But this is the data, and you can see the graph of the sock's position over time, and here you can see the position of the orange over time. Now, in order to model this, we used VPython, a program here, and how I started was with the initial conditions. I'd set the initial mass of the orange, or the sock, which was different for both cases. And since it started at the origin, because of how I chose my axes, I have it starting at 0, 0, 0. And because it's starting from rest, I also have the initial velocity as 0, 0, 0. Now my start time was also 0 because I chose to do that, and the time step I used to advance it was 1/30 seconds. The reason I did that is because Tracker here, where it captures between each frame, is 1/30 seconds. So I did that so the time intervals would match up. Let's see. Now, in order to model this correctly, I had to use the fundamental principle of momentum and the fundamental principles with drag. So you can see here where I'm getting the ball velocity and the ball position, I'm just using forms of the momentum principle broken up to give me position and velocity of the ball. The important part is that for F net used in these equations was a combination of gravity and drag. Now at first all that was done was gravity, and drag was just set to 0 so that it wouldn't have any effect, and we could see the difference in the models between what actually happened and what happens if you predict only with gravity. You can see in this, the blue is the observed path of the orange, and the red is the modeled path using only gravity with no drag. You can see the blue stops a little bit higher than the red does, because with gravity, the ball just keeps falling and increasing in speed. The same is true, but even more evident with a sock. You can see the orange is modeled with just gravity, and the blue is just the observed values we got from Tracker. And right here you can see it sort of straightens out right here and falls lower than the gravity model does. Now, secondly, we went in and modeled this, except we put in a value as 22, which was for the sock, and used that, which gave us drag values, which meant that the F net was now going to be less than just gravity because we're adding drag and gravity to get F net. And what happened with the models for that is that you can see here, this is the orange position, the blue is the observed, and the orange is what we got out of the modeling program. And you can see they follow mostly the same path and end up at the same point. The same is true of the sock position, where the modeled and the observed are both relatively the same, and they end up at the same position. And now for the question, what does it mean? For the object that drops slowly, examine the velocity versus time predicted by our models with and without drag, which models predict a terminal velocity. This is the graph right here of the model of velocity against time of just any object really, with gravity only being the red and with gravity and drag for force net being the blue. What you can see here is that the red, just gravity, it just continually decreases the velocity in a straight path because gravity has constant acceleration. And you can see in the blue path, it starts to go down the same path as gravity, but then slowly starts to curve out, and it wasn't modeled for long enough time to see, but it would eventually curve out to some point that would give us terminal velocity. So the model with drag is the only one that can give us terminal velocity, because the gravity-only model would just keep increasing and would never slow down. Because terminal velocity is the point where, drag and gravity are the same force, so that it's got a constant velocity. So you can't see the terminal velocity, but you can see that in the blue modeled with drag, it would eventually reach a terminal velocity given a long enough time. And for the what-if question, it's asking if you were to throw an object down, would it reach a terminal velocity, and to compare that terminal velocity with a case where it's just dropped from rest. To do that, I have the VPython program here, which is the same as you saw in the Word document. And what I'm going to do is I'm going to go in here, instead of initial velocity of 0, I'm going to give, say, a negative 100. So as if you're throwing it down pretty hard. And what you see when you run the program, it's got a graph here of velocity versus time. It's actually, the velocity is slowing down and it's starting to curve and it's leveling off here around, I don't know, probably about negative 20, negative 15 or so. And this is where it's reaching the terminal velocity. And if you remember that, now if you set it back from negative 100 and you set the initial velocity to 0 again, like we originally had it just being dropped, and you run the program, the velocity drops down from 0 and keeps going and slowly starts to curve and level out around the same point that it had from negative 100. So what does that mean? What that means is that the terminal velocities are the same whether you throw it or drop it from rest. It's the same for the object no matter how you throw it. In this case, we have to drop from rest. So both objects do in fact reach a terminal velocity, and it is in fact the same velocity. Thank you very much.